You have a question? Go ahead.
So on the lab, it for like one of the last questions, like it was the question that they didn't like. It was one of the multiple choice ones in the beginning. It
Mm-hmm.
was like, what is the tension at such an like what is the length of the spring at a certain tension?
Mm-hmm.
And in the beginning, it had you set it to spring two, but
That's
it never
actually
really
what that.
specified in the question
I
which
agree.
one to use.
I agree. So I actually started grading students and was able to more or less make sense of everything and pretty much grade it until I got to that question. And I was like, all right, the prediction part. So I saw there was a prediction, and then I went to the video because I thought it says in the actually it's right here. It's still in one of my tabs.
It said in the beginning of that
Yeah,
whole multiple choice section, like set your spring to spring two, because it was the tutorial. But on that last question, like I did the whole thing with spring two, but
yeah,
apparently it wasn't the right answer and it wouldn't let me
yeah,
change it. So,
It's something weird with that. So I wouldn't worry about it. I'll figure that out. But when I
okay.
look down at the bottom here, it says this last one: advance the video so the spring is stretched 40 centimeters. And then when I was like, all right, I'll do it myself, of course, and um, this one does stretch 40 centimeters. Oh yeah, that's what it was. So it's having everybody reference this video from what I can tell, which you guys can't even see because it's too zoomed in. But it's having everybody at the end, from what I can tell, use, it didn't indicate for you, it should have. So my point being, in the beginning, if you said, I'm going to use spring 4, then when you get to the very bottom, you should be choosing spring 4, right? Because your model, your equation that you created is based on the spring. And if you want to use it to make a prediction, then of course it has to be the same spring. They don't even comment on that here, which some students probably would miss. Moreover, there's a mention of stretching the spring to 40 centimeters. And I noticed there's some springs that don't even stretch to 40 centimeters, from what I could tell. If I load spring 3, is this one of the ones that doesn't even stretch that far? Oops. What happened? Clear? No, this one probably does. Oh, yeah, this one does. Whatever it was, I saw there was a couple that had strong spring constants that I don't think even got to the 40 centimeters. And remember, stretch, I already had seen that there's some students confusing the length of the spring with how far it stretches. Those are two very different things. When they say advance the video so the spring is stretched 40 centimeters, well, to me, I mean, I know it's kind of up to interpretation, but that means the physical stretched distance is 40 centimeters. I tried to clarify that for you back in the beginning, that it has an original length. Most of these appear to have been about 15 centimeters long in the beginning when they were just relaxed, when he's not stretching it, about 15 centimeters. So if they say stretch it by 40 centimeters, that means you'd go 40 plus 15 and you'd have to come to 55, right?
In that original question I was talking about, it also had odd wording for it. Like, so like it was like, what is the stretched length of the spring? And now they didn't really make it clear if they wanted like the extra
Yeah,
length that it stretched or if they wanted like the full length. And one of
yeah.
the answers, they had both answers. So it
Mm-hmm.
wasn't like you could figure it out by process of elimination. So
Yeah, and then I noticed just now, look at this, there's a comment here. Note, spring 2 and 7 do not stretch 40 centimeters, which is why no students are asked to collect data for those springs. To include those springs, have students make a prediction for value in the following ranges. So this is actually maybe just a note for me to see. It probably doesn't show that to you when you're logged in. But now I understand why 2 is missing. But again, the whole Hooke's law has everything to do with stretching a spring. It has nothing to do with how long the spring is. We're interested in how much force is required to stretch a spring by a given amount. That's it. That's all it's about. In the formula, F equals K delta L or delta X. That's Hooke's law. Delta is the change in length, right? How much extra length does it get to after you've stretched it? You may need, again, as I discussed earlier last week, you may need to very well reference the original length. If they tell you a spring is stretched to a length of 50 centimeters, to a full length of 50 centimeters, and its original length was 10 centimeters, now you have to think, all right, delta X is really 50 minus 10, so they stretched it by 40 centimeters, and that's what you would use in the math part, right? It's just a stretch, distance it's stretched. So just be aware of that. I did notice there's some students that appear to be confusing that, and that's a big difference, and it would throw off everything you're doing. Anyways, I'll get to grading that, probably start tomorrow. Just make sure you email me your spring so I know. Beyond that, we had the CK12, remember? CK12 again is here. So there's 3 CK12 assignments. I think the first one is centripetal acceleration, which we'll talk about in a moment. Thank you very much, Joey. The second one is centripetal force, which I'll also talk about a bit about today. And then the third one is gravitation and the concept of circular motion as it pertains to planetary motion, like the Earth going around the sun. Again, those were 3 assignments that are in CK12 right here. And you should be doing them in this order if you haven't already. Centripetal acceleration first, then force, and then this one is the last one. But again, those I thought were due last night at midnight, but they're not due till tonight at midnight. And then the last thing is I've decided to go for it and start Edpuzzle. This week, again, coming up, you guys are going to have a lab, like I already mentioned, but there's going to be other stuff. We have to move ahead. And in an AP year, I would always provide work to students during a holiday break. It's like a week and a half. You don't have to do it during the holiday. There's plenty of time in a week, in whatever, it's 12 or 13 days where a student can do work. An AP student should be, in my opinion. But I guess it depends on the class. Depends on how easy it is for certain courses to be completed in a certain amount of time. I can tell you in science, it's not so easy. In math, it's usually much easier. Most math classes can easily finish their curriculum and have a whole month to practice. In science, that very rarely happens. So even on a normal year, I would assign work. And this is not a normal year, so I'm definitely assigning something for us to forge ahead and gain some ground. You might think that means we're very far behind. We're actually not really far behind. If we are behind, we're maybe just a slight bit behind, just a tiny bit, really not a lot. As long as I keep moving forward, you stay with my pace and do the things I ask, we'll be fine. So just be mindful that I will be posting, I already posted videos that are Khan Academy videos, assuming that some of you have probably heard of Khan Academy, perhaps even all of you have heard of Khan Academy. The guy that does it for physics is very good, very, very good, excellent. Good at speaking, good at his drawings are wonderful, his math, everything he says, his describes, great, fantastic in my opinion. And that's not always common. A lot of times when I watch people describing physics, it's not always fantastic, especially on YouTube. Or even at a college and university. Sometimes you have really smart professors and you realize these guys can't teach. These girls, they're not meant for teaching. They're here because they're doing research, but they're not gifted teachers. Some of them are. In the vast majority of the cases, they're up at such a high level, as scientists, that they now have to come down to the level of a freshman in college to try to speak to them in a language that they understand. And some can do that, and those are the great teachers. Many cannot, to be quite honest with you. They struggle with it, and you have to really work. If you don't really understand it, you got to go into the book. You got to go to the tutoring center. You got to do whatever you got to do to make sure you understand it. All that said, this guy's great. It's fantastic. It's really great. Edpuzzle, if you're not familiar with that, is a website that tracks, if a teacher wants to assign a certain video, it could be any video on YouTube, it could be really any video at all, but I use YouTube. Then I assign it, now I can know whether you actually watched it. I can know exactly how much you watched. You're not allowed to skip. It pauses at a variety of times throughout and asks you questions that you have to answer. I'll know whether you answered them or whether you didn't. I don't know what you answered and all that kind of stuff. All the information is there. So it's yet another control for the teaching community to try to be able to have some integrity to the things they ask their students to do. Because without these controls, again, when it comes to watching videos, how do we know that you actually watched it? In a lot of cases, especially less than AP classes, CCSP or honors classes, they'll say they watched it, they didn't watch it. Some of them will have, but a lot of them won't. So that's the whole purpose of Edpuzzle. It's a brilliant idea, whoever came up with it. I'm sure they're making a ton of money because it's used by a lot of teachers. So when you follow that, it's all integrated through Google Classroom. It'll bring you straight in. It already, again, knows me and it connects with my Google Classroom. So it knows my classes, it already has your names there. And you're literally just watching the video. This is, you guys in class can't hear this. I can hear them. But anyways, there's some spots where it will stop and it will ask questions. And when you do get the questions, they're on the side, on the right side. It'll be very clear to you kind of how that all works once you're doing it. But just know that it's, you're graded on doing it, on watching it, and just did you answer the questions. Even if you got some of the questions wrong, I don't think it's that big of a deal. Usually the questions they're asking are fairly straightforward, so that if you watched it, you'll probably get them right. They're usually designed that way. They're not intended to be these super hard problems that only a couple kids are going to get right. It's usually just like a reading check. When you're reading a textbook, you read a paragraph, it says concept check. And it's like, we just described this. So what's the answer to this? And so kids that are able to engage and really focus on their reading, usually, yeah, I just read that. Get it right. So that's the idea of those questions. So those are assigned, usually they're less than 10 minutes. I think the two I just assigned are 9 minutes and 6 minutes. I'm going to assign a few more, again, to try to gain some ground through the circular motion unit. It's part of Newton's laws of motion, because it's actually known as Newton's laws of motion for circular motion. He developed his second law, F net equals ma for linear motion. He redesigned those same formulas to work for circular motion. So it's all part of the dynamics unit. My goal, again, was to have you gain some ground during the break, not enough to swamp you and really feel like, oh my God, all I'm doing is work. No, but we got to do more than 1 hour work or more than 30 minutes of work, so that by the end of the break, you guys have gained some ground in this unit, and we can kind of hit the ground running when you come back, where I can say, well, if you watch those things, you'll have already seen these things and at least understood these things, and we can kind of just move forward with those things. Otherwise, I'm starting from scratch. This is an opportunity for me to pick up a couple weeks, quite honest. So that's what we're going to do. Grab a day anytime I can on a year like this, or a week. So that's that. Any questions about any of that? All right, no questions about any of that. We are going to I'm going to ask you maybe to take down a little notes. You don't, I'm not forcing you to, but probably should. You want to get the main ideas. If again, it's not something that helps you understand what I'm saying, you don't want to, you don't have to. You know that I record these and I always post it later. You could always write certain things down later if you want. It's up to you. But I am going to write down a little bit for you to see, starting now. Strange. So something is, yeah, sorry, this is strange. Try again. There we go. Okay. All right. Where's my pen? Where's my pen? All right. So you can write down the words uniform circular motion. In a lot of textbooks, it'll just say circular motion. It really should say uniform circular motion. But even in the textbook that has a chapter titled circular motion, within the first paragraph, they're going to describe what uniform circular motion is. So let's just call it what it is. It's uniform circular motion. That's the whole topic. And right now, I'd like to describe what circular motion is and what uniform circular motion is. Circular motion, not very surprisingly, is any motion in which an object moves along a path that creates a circle. Some examples would be, a car going around a rotary, which, by the way, is the Pivot Interactive Lab that will start today, and you'll be asked to work on it over the break. It's actually not a very long lab. It's actually shorter than both the other labs. But, car going round and round a rotary is, well, from a bird's eye view, it's going in a circle. The planets that go around the sun, circular motion. There's plenty of amusement park rides, of course, which zip you around in circular paths. And you might even be able to think of some more. There's many applications, not usually in engineering, to be quite honest with you, because usually in engineering, building stuff, you don't want it to move. Everything you build in terms of bridges and all those things, you don't want motion. But there are applications, I guess there are applications, for example, in sports tracks for the high-speed cars. They're going around in circles at 200 miles per hour, and they have to bank. The actual road is not flat. It's actually an inclined bank. I don't know if you've ever noticed that, but for these high-speed biking circle path, circular tracks that you might have seen at like the Olympics, these bikers are biking on these like 10 speeds or whatever, and they're flying at high speeds, but you notice it's not, again, a flat road or not a flat track. It's literally tilted, always tilting towards the center. And they design those with a certain tilt on it so that it makes it an optimum way for them to move around the circle without having to skid out. So again, there's some of the references to it are a little bit obscure, which is true, but they're still out there. And truth be told, a lot of the so-called special problems we'll talk about are not necessarily practical. A common question here is a kid is whirling, a kid ties a rock to a rope on the end of a rope, grabs the other end of the rope and whirls it around his head like a lasso. It's a very common, problem that you just see turn up on MCAT or physics tests. Again, is there really any useful practicalness of that? Maybe not, but nonetheless, there's still laws of physics and you're going to be learning them now. So circular motion, of course, is any path that is circular, right? So I'm going to draw, let's use the example of the sun. So let's say the sun is in the center, and that is actually one big section that you have to learn. We do circular motion as an entry-level discussion, and some of the just concepts and formulas and things like that. But then there's a whole subunit on orbital motion, and then we'll end up with you need to learn what's called Kepler's laws. A guy named Johannes Kepler was an astronomer from I think the 1500s, and he came up with 3 laws of planetary motion, like Newton did. So similarly, but Newton did that later. Maybe he stole the idea from Kepler, the idea that somebody has their name attached to 3 laws. I'll make 3 laws and call it Newton's 3 laws of motion. Who knows? But there is a whole subunit on this that you'll have to learn at the end. So let's imagine this is the Earth, say, at a few locations. Conveniently, they always draw these locations at the cardinal directions, like east, west, not north, south. It could be anywhere, but let's just use these. So let's just say this is Earth, and I guess this is called Earth's orbit, which we're assuming in this discussion is a perfect circle. I'm going to show you in a minute using a simulation. It's not a perfect circle, but it's really close. So for the purpose of this discussion, let's assume that the radius of this circle, which is really the distance from the sun to the Earth, there's some distance here that we usually refer to as r for the radius. Notice that in the planetary model is literally just the distance from Earth to sun, right? When the Earth is up here, 3 months later, up at the top part of the circle, it's still the same distance r from the sun, right? If it truly is a circular path, which again, I'm telling you it's not. It's close, but it's not. If it truly was, then at any time of year, the length of this thing r, called the radius of the circle, would just be the distance between the sun and the Earth, right? The Earth moves with a certain speed, of course. The concept of it being uniform indicates, that's an important part right now, indicates that the speed doesn't change, because that's what uniform means. Something is uniform, it means it's not changing, it's staying the same. It's the same throughout. Like, again, uniforms that you wear at a job. Everybody looks the same. One form. Speed, so you might say, what are the criteria? There's circular motion, and then there's uniform circular motion. What's the difference? For uniform circular motion, that's what you learn mostly in this AP Physics 1, is circular motion where the speed does not change and the radius of the circular path does not change. Those things, what you would refer to as stay constant. As it goes around and around, at any moment in time, you can freeze it and draw R and say, well, it's the same as the last picture. We drew R, and it's the same as they're all the same. R, they're all the same. And the speed is the same. So for the Earth, for example, it's about 66,000 miles per hour. It's about the speed of planet Earth that you're on right now. How would you calculate that, by the way? How would you determine the speed of Earth?
Distance over time, maybe?
Good, absolutely. On the side, Jaden said distance over time. Well done. You would use distance over time, just generally speaking, as a side note. You didn't have to jot this down, but if you wanted to, this is just me on the side. But this will come into play for your lab. For the lab, the video is a car going around a rotary filmed by a drone that's hovering above the rotary. So what I'm talking about right now is similar. Speed is as long as you're referencing constant speed, and that's what we had just said, that the speed doesn't change as this thing goes round and round. Then if it was going along the circular path like this, there is some distance between 2 points in time, right? It's not a straight line anymore. It's what we call the arc length. It's the length of an arc. But that's still, if again, this was planet Earth going along its orbit, and we said, oh, let's just look at these 2 points in time here and here. Well, is there still some distance along there? It would be almost a quarter of a full circumference, right? If I drew it perfectly, it'd be exactly 1/4 of the full circle. And there's some amount of time that it took to go from here to here. You'd plug that in here. Or you'd say, oh, why do a quarter? What if it was just a whole, what if we had the whole entire circle? What would the distance around the whole circle be? The distance around a circle. Yeah. Yeah, just a circumference. So what is it? Yeah, so in this case, you can just say that the distance is 2 pi r, right? Or pi times d, diameter times pi, whichever you like to reference it as. And divide by time. That's just a little, I mean, it's in your text. You actually read about it in CK12. I looked to see if it was there. I wanted to see because it should be, and it was. It was good. The idea that a student needs to know for the circular motion when they're doing these motion problems, that when you're having to reference a distance, usually it's the distance all the way around the circle. It's just 2 pi r, right? They usually would give you r, and if they gave you the time, you could calculate the speed. What would the time for Earth to be? Well, how long does it take Earth to go around one full revolution? We call that one full revolution. Exactly, like, well, that's the year, 365 days, 0.25. Technically, if you wanted the speed in miles per hour, then you'd want to Google what is the distance between the sun and Earth in miles, and you'd plug that distance in for r in miles times 2 pi. And then if, again, you wanted speed in miles per hour, you'd have to figure out how many hours does it take the Earth to go all the way around the sun? Well, that's the same question as how many hours are in a year. You could work it out. You easily could work that out. That number would go here. And when you solve that problem, it comes out as 66,000 miles per hour. So more or less, the speed of Earth is pretty close to constant, meaning it's not going up to 80,000 miles per hour at some times and then slowing down to 12 miles per hour, 12,000 miles per hour. It pretty much stays at a pretty consistent speed. Again, there is some variation in speed, and I'll talk about that in a minute, but it's so close, like maybe the maximum speed is 67,000 miles per hour and the minimum is like 64,000 miles per hour. And you're like, wow, it only changes by like 1,000 or 2. And like, yep, it's just a tiny percentage of change in speed. It's almost the same value throughout. So that's what uniform means. Same speed, same distance from the center out. Now, the other important thing is velocity is a vector. You have to know that it's drawn like this. The velocity vector is always tangent to the circular path, straight ahead. If you froze again, if this planet was planet Earth drawing, going round and round this circle like this, I guess I've drawn the counterclockwise direction, and then right here when it reaches this easterly point of the circle, we say pause the video, and someone says that was Earth. Which direction is it traveling in this instant? It's instantaneous direction, maybe you would say. Straightforward. If the sun's gravity just turned off or the sun just bloop, vanished, which way would planet Earth go? There's no more pull of gravity, because why does it go around a circle in the first place? Because gravity, sun's gravity is always pulling it in, keeping it in this circle. Sun just vanishes. Isaac Newton said, well, my first law would take hold. An object in motion stays in motion in a straight line unless there are other forces to make it different. If you remove gravity because the sun vanished, there are no other forces. So which way will the Earth go? Just float away in a straight line in the direction of the velocity vector, because that's the direction it was traveling when the sun vanished. Of course, the sun won't vanish, but just trying to give you a sense of that. We call that the tangent velocity, V tangent. And the symbol you always see in textbooks and on the AP exam is VT. They almost always put a capital T. Lowercase t would still mean the same thing. For whatever reason, you often see a V with a capital T as a subscript. That stands for the tangent velocity. Because what does it mean to be tangent? If I draw a circle like this and someone says, here's point P in math class, draw the point of tangency. Well, I didn't mean the point of tangency. Draw the line that's tangent through point P at this point of tangency P. You would draw it like that. That line is tangent to the circle. to the point P on the circle. If someone did this, is that tangent? No, it intersects. It actually intersects right here, and it intersects the circle here. That's violation. The whole idea of tangency is that a line touches a point. This line touches this point on the circle, but it doesn't actually intersect the circle. So you can draw tangent lines just like that, like a bubble. If it was a bubble and you had a little pin, you lay the pin. If you intersected, the bubble will pop. That you'll know that you weren't doing a tangent. If you lay the pin right on the bubble, then it should kind of float on or stick on it like that, tangent to the bubble. So for that reason, again, we call that the tangent velocity because it's like that. It's perpendicular to r at all times, right? Over here, the tangent velocity would be this way. Down on the westerly side of this circle, the tangent velocity would be straight down, and so on and so forth. I mean, I could draw the last one in. If it was at the southern part of the circle, then the velocity is rightward or eastward. But my point being, is it always perpendicular to r? At this point, if it said the Earth is over here, you say, okay, I'll draw r, and there's r. That line r and the tangent vector, 90 degrees. You could draw a little if you wanted to. 90-degree symbol. How about at the top? R, VT, yep, 90 degrees, right? These are always worth pointing out. VT is always perpendicular. It's always perpendicular to r if it's truly circular, perfectly circular motion. I'm going to go off a little bit on the side just because I think I want to. Oh, let me minimize this. There's so many things. So give me, oh, it's already on. So here is, here's a simulator, which is a fantastically powerful and wonderful simulator known as the Worldwide Telescope, made by Microsoft. I think they spent over 10 years making this, which is amazing that they offer it for free. It's a big file. I think it's somewhere upwards of 50 to 70 gigabytes, which for PC gamers out there know that a lot of games these days are that big, because the amount of information necessary to represent all of those details and graphics is phenomenal. But if you do have a PC at home and you love space stuff, I'd say go for it. If you got space on the PC, it's really a cool tool. If you like space stuff, it's free. Again, it's called Worldwide Telescope. You could Google just WWT, and you'll be brought to Microsoft, and there's a free download there, or Worldwide Telescope. So this is, I'm just using to have you again just visually see what the solar system looks like. Why not look to nature? You know, when you're trying to understand something, or trying, especially in physics, right? Physics is all about the physics of nature. And everything we do is usually, not always, I shouldn't say everything, but in a lot of cases, a lot of the things we've learned, not just in science, but in math, was first learned by looking at nature. And it's not just now, you're talking thousands of years ago when they were figuring out this stuff. And there was phenomenal amounts of information known. The Great Fire of Alexandria in Egypt, there was a library there that housed countless amounts of, or not countless scrolls of the time. And these scrolls had tremendous knowledge. And some of the things that were found say there was some sort of people that imparted this knowledge to the human beings. That's a whole nother discussion. You can ask Joey about that one. Yeah, I said the Alexandria, the Egyptian library in Alexandria, which housed a lot of ancient scrolls that were said to have had phenomenal amounts of scientific knowledge, far beyond what they should have understood at that time. And I said there are some theories that that stuff was potentially given to them by some race of people or whatever it might be, but that's a whole nother topic. And I said you could ask Joey about that. The who are they? Do you remember? Who was the name of them? You remember? The Anunnakis, yeah. Anunnakis, fascinating. Yeah, in Sumeria, the most ancient civilization known to man, far older than Egyptians. Anyways, my point is they knew a lot of stuff back then, and a lot of the stuff they had learned was from nature. So it's always a good idea to look at nature. Even today, when they're making robots, these computer, scientists and programmers and robotic, people that come together in teams, usually they look at nature first to figure out if they can mimic like a spider, for example, how it walks. Like, because if you can make a robot that walks like a spider, like it's pretty cool to have 8 legs and be able to walk like it does. So nature always provides good examples of this example of that. So there's this uniform circular motion. You can see as I zoom in all the way to the center, you have the sun, of course, in the center. And then when we zoom out, there you're seeing each of the orbits. Now, at first glance, they do appear circular, right? But remember I said that they're not actually perfectly circular orbits, and it's not exactly uniform circular motion. Here's why. If the orbital motion of all the planets in our solar system was uniform circular motion, the center of the circle, which is actually a little above the sun would have to be at that central point. But it's not. Johannes Kepler, which you learn about later in this unit, and you have to again learn his laws, his first law was that no planetary motion of planets around a star will ever be perfectly circular. They'll always be slightly off. They'll always be what we call ellipses. If you wonder what is an ellipse, ellipses look like a squashed circle. You may have learned about them in a math class, I don't know. More than likely some of you have. The ellipse has 2 spots which are called foci, which I'm pointing to with my mouse. 2 foci. And you can create an ellipse by physically, let's say, taking a piece of wood, laying it down, taking a nail and a hammer and nailing a nail into here with a hammer and nailing a nail into the other spot with a hammer. Tie a string that goes from here to here. And then take a pencil and bring the pencil into this little area and stretch it out with your pencil so that it forms a triangular shape. And then hold the pencil with the string like this and swing the pencil all the way around, and it will form a perfect ellipse on the paper. That's how you draw an ellipse. And how squashed vertically the egg shape is depends on the position of these foci. These are called a focal point. Together, they're called foci. And they're a property of an ellipse. And so if you imagined taking these areas where you place the nail and repeating this experiment over and over with drawing ellipses, but each time you move the nail here in by a few inches and then you move this nail in by a few inches and you repeat it, you draw this pattern. It's a little less elliptical, a little more circular. Next time, bring the inch a few more in, bring this nail a few more inches in, do it again, a little more circular. At some point, these 2 focal points merge together at the center, in which case, if you did this, you would just have 1 string and 1 pencil coming from that, and it would create a perfect circle. Showing that in order to have something that's circular motion, you literally, for planetary motion, the sun has to be directly in the center. And Johannes Kepler said it's not possible. All stars, he said, star systems will have the sun at one of these foci points. And so when we go back to this image, you'll see that if the center was supposed to be here, that means 1 focal point is here. And again, if the center was supposed to be here, the other focal point would be the same distance, but above it. And those would be the 2 focal points. And he said, well, your star will always be at one of those 2 focal points, which means I'm just pointing out that even though this is very close to a circle, and without knowledge of that, most people look at it and say, yeah, it's circular, especially when I zoom out. Yep. A little louder. Just an empty point in space. Yep, nothing's there. Good question. The question Emma had was, what is there something at the other focal point? There's never anything there. It's just an empty point in space. But the sun will always occupy one of those points. Good question. And then again, when you zoom out, you see that these definitely look like circles. So these are all the orbits of our planets. And to a very close approximation, I'm telling you, it really is really close. So if we said like 100% represents a perfect circle, and you said what percentage is like the orbit for Earth, it's probably like 98% a perfect circle. There's like a little error in the squashness. It's so minimal you wouldn't even notice it, and the sun is just so slightly nudged off to the side of the center that you wouldn't notice it. So for that reason, it's okay for us as teachers to teach uniform circular motion and then go into a whole unit on this and say, we're going to apply this here because it's so close to being perfect uniform circular motion that it's a good model to use. If you truly wanted to go to become an astronomer, you would have to learn the true details of elliptical motion and all the other math that goes with that. Okay, I'm going to return now. Oh, I would say one other thing, actually. If we look at Earth, or let's just look at Mercury. Mercury is fairly eccentric. Eccentric means that it's the sun is fairly far from the center. The only one that really matches that would be, it's called the eccentricity. The eccentricity is how far off the sun is. So this is actually Pluto. Pluto is the white one. And you can see the center of that white circle, which is Pluto's orbit, would have been here. Look at how far away the sun is, right? Means this is really an ellipse, because as Pluto goes around this, there's times where when Pluto's over here, it's much, much closer to the sun than when it's all the way on the other side of the orbit. Look how much further away that is from the sun. There's a huge difference there. It's highly eccentric. The eccentricity is when it's high, it means it's got a big difference on distances on both sides. My point being, for the inner planets, Mercury has the highest eccentricity. And when you're looking at it, I just wanted to point out, like, this distance going from here up is much larger, in my mind, from what I can see, to the distance that goes from here down. So that means is, remember that, think about a basketball. When you throw a basketball up in the air, it's going further away from the planet. So what's happening to its speed? When you throw a basketball and it's rising, 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 and you're tracking its speed as it rises, does it speed up, slow down, or go up at a constant speed?
Slow down.
Slow down, because the energy that you had in kinetic energy when you released it is turning into potential energy, gravitational potential energy, as it gets higher and higher and higher. So it slows down. As it returns, gets closer and closer to the Earth, that potential energy turns back into kinetic energy, and a closer and a closer approach for the basketball to the Earth results in faster and faster speeds with the greatest speed at impact. That same idea plays out here. So when the planet, and this is worth you hearing, because this is sometimes a multiple choice question on the AP exam, they show a picture just like this and say, where would the planet be moving with the greatest speed? They'd say, here's an image of, they actually have ones that are not uniform circular motion. They say, here's an ellipse, because they're assessing Kepler's laws, your understanding of Kepler's laws. Where is it furthest from the sun? Here. So that means as this planet Mercury comes around like this, it's going to actually lose speed, because it's actually getting further in distance each time it goes along this arc, further and further away. That's like a basketball rising. It slows, slows, slows. Be actually moving with its slowest speed here. As it comes through this point, now these distances from here to here, and if it's here, it's a distance from here to here. Those straight line distances get smaller and smaller and smaller, which means it's going to speed up, speed up, speed up, speed up, speed up. And then after it passes somewhere around here, the distance will again start increasing a little bit. After actually here, I think the lowest distance is here. So you end up having this slowing effect up when it's far away, and then speeding up effect when it comes around the bottom. And that was me wanting you to understand when I said orbital motion isn't necessarily uniform. It's not just because of the fact that the distance r is actually different at different times of the year for Mercury. These r's aren't all equal. But if the r isn't equal at all points, then the speed isn't equal either. When r is small, the speed is high, while where r is big and it's far away, the speed is low. So both of those properties change, which totally violates the criteria for uniform frequency. All right, I'm going to return to my paper if I could. I'd like to talk about centripetal acceleration, if I could. Centripetal acceleration is, we've established some of the main ideas. I think now let's tackle some of the, well, we've tackled some of the main concepts, I should say. And so now it's time to kind of tackle the first main idea. It's called centripetal. It's not two words. I just maybe sometimes do that just so students can really see that word centripetal. One word, no hyphen, one continuous word. Centra means like center, and petal means seeking. So when you hear about centripetal force and centripetal acceleration, which was part of the CK12 assignment, it's referring to some sort of force that causes an object to move in a circular in a continuous attempt to seek out the center. You think of it that way. If you're moving around something, it's like you're focused on that center. You're feeling like you want to come in, but there's other forces of nature that prevent you from getting closer. But it's still an attempt to seek out the center of the circle. So it's called centripetal acceleration. This is where it gets confusing, and this is where it's worth a teacher taking the time to teach this, because When you think about acceleration, most students would say, wait a minute, acceleration is when you speed up or you slow down. And you just finished telling us that uniform circular motion, the speed doesn't change. I'd say that's true. And you'd say, then what's centripetal acceleration doing here? You know, why isn't it the word acceleration coming into this discussion? If you just said again that uniform circular motion is our topic, and it goes round and round and round with the speed never changing. Yet section 1, centripetal acceleration. And this again is the confusing part. Acceleration, remember, is a change in velocity divided by a change in time. It's a time rate in terms of how rapidly the velocity changes. However, acceleration is actually a vector and velocity is actually a vector. Reminder that velocity and speed are not the same. Velocity includes, velocity, which is a vector, includes speed, which is technically called a scalar, it's just a number, not a vector, and direction. There's two components to velocity. I can bring that a little closer. Velocity has two bits of information, speed and direction. It's a vector. And again, what you call magnitude of velocity, I guess, magnitude. Magnitude of velocity is called the speed. It's the length of the vector that I was just drawing in that picture. And I was drawing those, who knows, I lost that page at this point. Move everything around. Remember that the length of this is the speed. It's the magnitude of the velocity vector. Magnitude is length. So my point being is that since velocity is a vector, and let's just I'm going to draw a little portion of a circle like this. If something is going in this direction here, I'll write VT with a vector symbol over it. And then maybe a little bit later, I'll put the object here. And this is moving around, I guess, counterclockwise again, my drawing. It doesn't matter which direction you go, counterclockwise or clockwise. But I'm just trying to show something that's moving in a circular path, moving in that direction, so that if this was, point 1, then later on at point 2, if we said draw the velocity vector, well, it will be tangent. Same length though, because we're talking about the same speed, right? Speed's not changing, just changing in its direction. But my point is, if we look at these two velocity vectors, did the velocity change? Originally, students who are only thinking that velocity has to do with speed say, no, the velocity didn't change. And then you, as a teacher, have to say, I have to remind you that velocity is actually a vector. It has two parts to it, speed and direction. So true. If the speed is changing, is the velocity changing? Check, yes to that. We call that acceleration. If the speed is not changing, but the direction is changing, is the velocity still changing? Well, if the velocity is a vector, if it didn't change, then these would be in the same direction, both in the same direction. Two vectors that are in the same direction represent a vector that didn't change. They're in different directions. They're two different vectors. So did the velocity change? Yeah. In length? In magnitude? In speed? No. In direction? Check. Yes. It changed in direction. So that means just a change in direction, even though the speed is not changing. Again, it could be a car going around a rotary, which your lab will be like. Car goes round and round at the rotary at 50 miles per hour the whole time. Speed's not changing, but the direction is changing. Or planet Earth going round and round and round at about 66,000 miles per hour. If it was always that speed, speed's not changing, direction is changing. In all those, or both of those examples, if the direction changes, the velocity changes. So if velocity direction changes, it's accelerating. Because acceleration is defined as any change in velocity as a vector quantity divided by how long it took for that change to occur. When we're talking about linear motion again, which is how much did the speed change per second, that you already done that. Now we're talking about how much did the direction change? How rapidly is the direction changing? So if velocity changes, it's accelerating, and we call that centripetal acceleration. It's a rate. It's the rate of change for the direction of velocity. Or in simpler words, how quickly is direction changing? That concept, how rapidly the direction physically changes as it goes around this loop, is called centripetal acceleration. It has nothing to do with speed changing. It's all about how quickly is the direction changing. We call that the centripetal acceleration. And this symbol C stands for centripetal. And not surprisingly, A stands for acceleration. We call it the centripetal acceleration. So with that laid down, that idea laid down, let's look at two scenarios. Let's look at one scenario where maybe a little boy or whatever, a little kid is going around a circle in the driveway in his bike. He's on his little tricycle and he goes round and round. He just likes going in circles, round and round. And let's just say, this is a path for a bike. Kid always travels at 5 meters per second. So every second, he moves 5 meters along the circle. The path for a bike. This is a top view. Top view. And know that in a lot of this stuff, when people teach this in textbooks and simulations, they show the top view because you're trying to see the circle. He always moves at 5 meters per second, let's just say. Just for clarity, that means that he would move 5 meters along that path in 1 second. That's still called 5 meters per second. It's not a straight line distance of 5 meters in 1 second. It's now a distance along the circle. It's called the arc length. You want to know that? It's called the arc length. The arc length is the length that can be transcribed along a circle. Arc length. But the idea still holds. If you're going along a circle at a speed of 5 meters per second, in that second, you'll move 5 meters along the circular path. Let's compare that to the kid the same kid, decides he's going to, on the next day, he's going to do the same thing, top view, path for kids bike, path for kids bike. And the same thing, he always moves at 5 meters per second. That's just how fast this kid bikes. He likes to go at 5 meters per second. And so now let's just draw in a couple scenarios. Here to here. And let's draw those same two in on the bigger one. Here to here. So in which circular path do you think his direction will be changing most quickly? Remember that when we compare the two scenarios, the speed is the same. He always rides at a bike speed of 5 meters per second. He's either on Tuesday riding around this big circle on his driveway, or on Monday he's riding around his tiny circle. But in both days, he goes 5 meters along the circle in 1 second. In which scenario do you believe, let's call this scenario A and the other one scenario B, in which scenario do you believe his direction of motion is changing most rapidly?
Scenario A.
Scenario A, yep, exactly. Especially if you really expand this, imagine that this circle is now the width of Earth's orbit. In 1 day, Earth goes from here to, 1 degree. It's 365 days, and it's 360 degrees in a circle. So more or less, Earth moves 1 degree per day. So if Earth was here, then the next day it's here. How much did the velocity change in direction between Tuesday and Wednesday? You'd be like, not much. Draw the velocity vector for Monday. Draw the velocity vector for Tuesday. Aren't they kind of like the same? You're like, yeah, because the circle's so big, right? The direction of motion is changing so slowly. That path is a massive circle. You're not going to move that much along it, even if you're going at 66,000 miles per hour. However, when you shrink that down, this thing go round, 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 round. This thing is traveling east, or west, I should say, here. South is traveling here. East, over here, it's traveling north. Think of how rapidly that direction is changing if it's a small, tight circle. Right? So the velocity direction changes quickly, or more quickly, I should say, when r is small. when I can make a similar comment here. I'm sorry, I didn't mean to say R. Velocity direction changes more slowly when R is big. Remember, R is just the radius of the circle. So I've established that the centripetal acceleration is how quick is a word, a fancy word for how quickly the direction changes. And we're going to need an equation for it. Does the centripetal acceleration, how quickly the direction changes, depend on the radius of the circle? We've agreed, yeah. So the formula for centripetal acceleration, labeled AC usually, is proportional to, it has to include R. The radius of the circle has to be in there because it depends on R. If R is really tiny, like we said, then the direction changes quickly. We call that a high centripetal acceleration. If R is big, on the other hand, and R is changing very slowly, if R is big, on the other hand, and the direction is changing very slowly, then we'd call that a low centripetal acceleration when R is big. So where do we think R should go? Here or here? In the denominator. Why would you like it there? Because they're inversely proportional. You're starting to speak my language, actually. I like that. AC is inverse, AC being the centripetal acceleration, how quickly the direction changes, is inversely proportional to R. What does that mean? A smaller radius is higher centripetal acceleration, meaning direction changes more quickly. Or vice versa. You could make the opposite statement, which is a larger radius has a lower centripetal acceleration. Direction changes more slowly. This is something Isaac Newton figured out. I mean, even if you guessed that this was true, how do you know if this is raised to the 1 power? How do you know if it's squared? How do you know if this is an R cubed? Mathematically, how do you know? How would you know what nature has chosen for this particular relationship for circular motion? You wouldn't. You got to be brilliant scientists. A lot of people that are not necessarily brilliant scientists could probably rationalize this out if they had some math skills. But then when it comes to how do you know what power this is, that takes an Isaac Newton, in my opinion. Somebody very gifted to think about this sort of stuff. What's the only other thing that would affect how quickly the direction changes, other than the geometry, which is the size of the circle? Well, if this is an ant crawling along this circle versus little Billy, other than the size difference between ant and Billy, what's the other major difference between ant and Billy? The speed or velocity, yep. If you're zipping along, doom, 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 that direction is going to be changing very quickly. If you're an ant, of course, then the direction is going to be changing very slowly. So this has to have speed in it. Speed has to be considered when you're thinking about how quickly this direction changes. Where would that go? Well, more speed would mean higher acceleration, higher rate of change of direction, right? So V has to go in the numerator. The only thing that, and I'll comment there, maybe add that note here, AC is proportional means more speed, higher centripetal acceleration. AC is proportional to V, and this took an Isaac Newton, V squared. Because again, with science and math stuff and physics, you never know what the exponent's going to be. It's never 1.2, it's never 2.32. The exponents are always integers. Nature seems to prefer integers by far, because it's always a whole number. But the question still becomes, how do you know if this is a R cubed or an R squared or an R2, 3, 4, whatever the number might be? That could become a very challenging experiment that you'd have to do to tease that detail out. Isaac Newton figured out that it's a V squared. So this is the formula. It's a centripetal acceleration. V squared over R, where V just represents the speed. It's super easy to use. R represents the radius of the circle. Centripetal acceleration. That's AC, and R is the circle's radius. And then think about it this way. If you're on the highway and you have now 2 off-ramps, one that goes like this, and another one that goes like this. And you said, is this circular motion? Well, even if the road goes out this way, then yep, as long as I can transcribe a circle in here that ends up fitting along that part of the road, then the car is in circular motion during that part of the road. And I guess if it was bending out the other way, you'd say, well, I'd have to be able to kind of draw in a circle that kind of matches right here. So, and there's R, or there's R. Or this giant one. Whew. So this is the highway, and your car is driving this way, and you can either get off this ramp or this ramp. And in both cases, you're going to get off at 50 miles per hour. In which case would you slide sideways and hit the side of the door more quickly? This one? Does everybody go, oh, slow down? Or in this one, does everybody say, oh, slow down? Which one does everybody say, oh, slow down on? If you go off both of these at 50 miles per hour.
The right side.
Yeah, the right side, right? Why? Because your direction is changing very quickly there. And since your car's direction is changing very quickly, but your body's is not, while in the car, your body tries to move in a straight line, while the car underneath you tries to stay along the curved path. That causes your body to collide with the side of the door. And that whole leaning effect, it's your body trying to fly off in a straight line. And of course, your car is preventing that. Your door is there saying, no, you're not allowed to go flying out. You're going to stay in, and you feel pressure on the side of the door and on your shoulder. So just giving you that sense of sharp turns are often considered sharp because their radius is small. And that means this immediate suggestion that this direction is changing real quickly. And that's why everything's flying off and hits the side of the door. Or, coffee spills off the dashboard. It's more likely to spill on this one, and less likely to spill on this one. All right, the last couple notes I'm going to make, I know I'm almost out of time, but do the best I can. The last couple notes I'm going to make is centripetal force. Centripetal force is the force needed bad wording, sorry. It's the amount of necessary force in the inward direction. I'll explain inward in a minute. So that the object stays on the circular path. This requires force. In order for something to change its direction of motion from straight, like a boat that's like drifting straight ahead, and you're like, turn the boat, like we need to go that way, you need to go. Well, it's going to take a force. You need to turn the wheel, the propeller behind is going to start turning. It's going to put a force from the water on the propeller. And it's going to start steering the boat, in a certain direction. It always takes a force to change the direction of something's motion, even if the speed's not going to change. And for this topic, that force is always pointed towards the center of the path. It's called the centripetal force. Same symbol, C for centripetal, F for force. The centripetal force, it's always an inward pointing force. It's a center seeking force. Again, this was the Earth example, and this is the sun, I suppose, and this is Earth. Then at all points along the circle, if someone says, draw the centripetal force vector, it has to be in. In the real world, what force provides that? This is really the sun and this is Earth. What's pulling the Earth in at all times towards the sun? The gravity of the sun. You're like, oh, that's so convenient. Like, the sun is always pulling it in? Like, yep, because the sun is an attractive force. No matter where it is, the sun's gravity is always pulling the Earth in. Like, oh, that's the centripetal force that's needed to keep the Earth in a circle? Yeah, exactly. Totally. And if the sun just vanished again, then when it was here, it would just, if the sun vanishes when the planet's here, it just goes off in a straight line. You need that inward tug to stay along this path. It's called centripetal force. The nice thing is that since Isaac Newton already said, hey, I already figured this out for linear motion, then the centripetal force formula must be the same. The centripetal force must be equal to mass times the centripetal acceleration. He said, hey, I already figured this out, that a mass times an acceleration is a force. So if you want me to make new laws for circular motion, and we'll call it Isaac Newton's laws for circular motion, then the centripetal force must be equal to the mass of the object that's going in the circle times that rate of direction change, which we actually just said was v squared over r. So the typical formula showed in a textbook is mv squared over r. You could put magnitude symbol around that if direction is not of interest, which in many cases it's not. I just want to know how much inward force do we need to continue applying to this thing to keep it going in a circle. Tell me what its mass is. If it's heavier, it's going to require more inward force to keep it along that circle. What is the speed? If it's moving faster, then it's going to require more inward force to keep it in that circle. What's the tightness or wideness of that circle? If it's a tight little circular path and r is tiny, it's still going to even require more force to keep it changing its direction so quickly. That amount of force depends on all three of those quantities. All right, that said, I would like to change my gears to show you this lab. I don't think I'm going to write, well, I might write a little bit down, so don't put away your stuff, but I want to at least show it to you. So I have assigned it, it's not due until after break, but I want to at least show it to you. It's a drone that's been hovering, was used to hover over a rotary. And let's see what it looks like. So when you play it, the drone is recording this. You'll see that there's, of course, cars going at a constant speed because this is a constant speed. It's a uniform motion lab. You'd notice if you looked closely, which you may or may not see, there's an X on the roof of one of them. The X is the one that you're tracking. These guys are just there because they're going somewhere. But these guys are part of the experiment. They're part of this whole company that's doing this. They put the X there so that you could watch that this is the car we're watching. And it's going to go around and around at a constant speed. How do I know? Well, I could count. How long does it take it to go from here to the left side over here? Let's see. 0, 1, 2, 3. All right. If it's a constant speed, it should take 3 seconds to go from here to the bottom point. Let's see. 0, 1, 2, 3. All right. Constant speed. Same distance, same time. It's a constant speed. What are the tools? You got a protractor. Protractor can be used to measure angle if you wanted to. It's like you would say that the car is at an angular position. Oops, he left, he's leaving. The car is at an angular position of 330 degrees right now. The car is at an angular position of 0 degrees. So in a little while, not right away after break, but within a few weeks, we start talking about angular rotational motion. And this idea comes up that you can describe the position of something as an angle or as it moved around the circle. At a position of 60 degrees and so forth. So that's a tool. You have your meter stick. Notice it's not really a meter stick. It's like a meter stick, but it's a giant meter stick. This is 5 meters, 10 meters, 15 meters, 20 meters. These are real distances that they've calibrated for the real world. This is the true distance. So this is what you would use to measure what? The radius, r. Good job, Emma. Yep. You would use this to estimate the distance r from the center out to where the car is. Of course, you have your stopwatch. Now, you might say, what would we use the stopwatch for? It's reminding you that you can reset it at any time. Well, remember that there's the v squared over r. Well, what is v? Jaden said to me in the beginning of class that if it's constant speed motion, he said distance over time, right? And we said, that's right, distance over time. Distance was circumference, 2 pi r. I just showed you how you'd measure r. So, okay, 2 pi r divided by time. You're going to have to time that car, right, using your stopwatch. So technically, you can get distance and time measurements, work out the speed, v, giving you access to v squared over r. Multiplying that by m gives you access to the centripetal force. The overall question, which is why, again, this is not a long lab. There's no data sets, there's no graphs, there's just one question. And then one conceptual question, and that's it. Relatively short lab. It says, notice, that this van has an X on it and such and such. The driver of this van was experimenting by driving the maximum speed while the wheels began to squeal. So if you've been going around a corner too quickly with a car, you're going to hear those wheels start to go, you'll hear a squealing sound. What that means is that the frictional force that's keeping your car on that path is getting maxed out. Remember, static friction has a maximum value? Well, I'm going to ask you to jot this down. I reckon if I have, hopefully I can squeeze it in. If I don't and we run out of time, then I'll post it online for you. But try to jot it down. For a car that's going around the rotary, the inward force is actually the static friction force, FFS. It's not sliding because cars aren't sliding while they drive. We can talk about the details of that later. I'll agree it's confusing. We'll talk about it later. Just trust me right now that the force for a car that has wheels traveling in this direction has a force that's perpendicular from friction. I know it doesn't seem to make sense, but just trust me that it's true. You can read about it in your textbook. The static friction force between the asphalt and the wheels is actually this way. It's equal to, it is the centripetal force. It provides the inward force at all times so the car can navigate the turn. If it hits a patch of ice, well, what happens to friction? If it's really slippery ice, this goes away. Which way does your car go at that moment? Crash. Goes in a straight line until it crashes. As long as that inward tug from the road is always pulling in, the car can navigate the turn. That's called traction. What is the maximum static friction force? Do you remember? Coefficient times the normal force. Well, what would the normal force be for our car? A parked car? Sure, mg. How about a car going in a circle on a flat road? What's the normal force? Well, still getting pulled down with mg, so the road has to push up with mg, right? As long as the object's not moving up or down, then the normal force is mg. So in this lab, I'm not asking you to, recommending you write this down. This will be totally helpful for you. The maximum static friction force is mu s times m times g. Since we had this already built, that the centripetal force is mv squared over r, we already did all that. The amount of inward force necessary to keep this car along that path. The road has to be able to provide enough friction force to equal whatever the mass of the car is times the speed that it's moving at divided by the radius of the rotary. If the frictional force can match that requirement, you're good. You won't skid out. If this number computed comes out as 10,000 newtons, yet the static friction force says I can't go more than 9,000, sorry. Well, if you're going that fast and the requirement is 10,000 and it can only offer 9,000 of inward amounts of force, you're skidding out. So the point is, as you get faster and faster and faster, this value, this requirement grows because V gets bigger and bigger and bigger as you go faster and faster on the rotary. At some point, this amount reaches the maximum that static friction can provide. And that's when you start hearing the wheels squeal. It says, I can't go more than that. I'm at my maximum. If you even go a half a mile per hour faster, I'm letting go. You're going to skid out at that point. You can't go around a rotary at 10,000 miles an hour. So these are the same. We set these equal. The centripetal force it is the maximum static friction force. FC, the centripetal force it is that. Whatever's pointing in as a force, it is the centripetal force. So you get to say mv squared over r, and then you get to put the mu s times mg over here. This isn't an answer, or this is just what you need to use. What question did they ask? They actually asked you, based just on the video that I showed you and your tools, determine the coefficient of static friction between the road and the wheels. This is actually one of those special problems. Sometimes turns up as a free response question on an AP exam. One they like. I don't know why they like it, but they like it. And so technically what's going to happen to the M's? They're going to cancel, which is why there's no scale tool to measure the mass of the car. It doesn't matter. How will you measure V? As Jaden said, distance over time, which is technically 2 pi r over t, right? You can do 2 pi r over distance over time, 2 pi r over t, because the distance is the distance around the whole circle, divided by how long did it take to go around the whole circle. That gives you a measurement for V. You just square it. R is measured with the meter stick. You know what G is. The only unknown becomes the coefficient of static friction. That's the question. That's the only prompt they provide. Based just on this video, make whatever measurements you have to do and calculate the coefficient of static friction in this text box below, explain, show everything you did. That's it. I helped you out because, well, it's on break. I'm not going to be necessarily available to help you like I would want to. So I don't mind giving you that direction. But just know that this, again, is one of those special common problems that turn up. And I know I did it quickly, but I think that I'm going to provide some more resources to you at home. Not to mention, the Khan Academy guy has an 8-minute video, which is really good, which is about this problem, which I'm going to be posting as well. So there should be, thank you very much, Mark, I appreciate it. There should be enough resources for you in addition to what I provided here. for you guys to tackle that. Again, it says, right here is the only question. Using the information, determine the coefficient of static friction. Last point is that if you want to do it on paper, I think it allows you to upload right here. Take a photo with your phone. I think this little icon should let you do that, I think. If you don't want to, or it doesn't allow it, or there's some error with that, then you'd have to type it here. And then there's one conceptual question here, which I'm going to let you guys think about on your own. That's it, though. There's no graphs. There's no data tables. It just, here's a video, make some measurements, see if you can calculate this thing, this coefficient of static friction. So we're more or less out of time. I obviously will post this. I did record it. And just reminding you that there's the Khan Academy videos. Again, they're all going to be circular motion. Again, usually the unit starts off with earthly problems, like this is what I call an earthly problem. And then after a few earthly special problems that are common on an AP exam, we move into planetary stuff. We go back into the orbital motion and planets and how that all plays out with circular motion. I don't know that I'll ask you to do much with orbital stuff. Probably we'll tackle that after the break, but I do want to kind of move through the beginning part of this unit, what comes before the orbital motion, as much as we can. So again, look on the Google Classroom. There is some stuff already there, but I'll add some things for you guys to try, and some other resources too to help you out. And this is in your textbook. You know, you could always after the Newton's laws of motion chapter in your recommended text, the next chapter says Newton's laws for circular motions. And any of these problems that I referenced, they're in the textbook. They have examples because they're the special problems, and they already have examples showing how all this stuff is done. So that's where you would look for additional help. All right, any questions from anybody at home? Time. I will not see you because I think it's periods 1 through 4 for shortened periods. So I hope you all have a wonderful and restful, enjoyable, safe, healthy holiday break with your family. Definitely enjoy it. Hopefully you're not going anywhere. I do hope that. If you are going somewhere, traveling, then I hope it's somewhere that there's not much risk, because it is a risk. If you have to do it, you have to do it. And then make sure if you are doing that, then you got your mask on and you do everything you have to do to keep everybody in your family, including yourself, healthy. So happy holidays to everybody. Whatever holiday it is you might celebrate, hope you enjoy it. Let me know if you have questions. You can always email me. All right? Otherwise, I'll see you after break. Bye, everybody.
Mr. Kurzak.
Bye-bye, Jaden.
Bye-bye.
Bye-bye.